Assalamu alaikum students. Today's topic is going to be about numerical of the chapter gravitation. Let us start with our first numerical, which says find the gravitational force of attraction between two spheres, each of mass 1000 kilograms. The distance between the center of the spheres is 0.5 meters. The answer should come 2.67 into 10 to the power minus 4 newtons. So here we have two spheres, this and this, and they are separated by a distance of 0.5 meters as shown, and each of them has a mass of 1000 kilograms. Now they are moving close to each other, that means the force of attraction or gravitation is between them, and we have to find that force, which is F. Now the data which is given to us is the mass of the first ball is m1, which is of 1000 kilogram. The mass of the second ball is also 1000 kilograms. Distance between the center is 0.5 meters as shown over here, and the gravitational force is taken to be a constant, so it is 6.67 into 10 to the power minus 11, and this is having a unit of a Newton meter squared divided by kilogram squared as shown. Yes. Now in this case we have to apply some formula for it. So to find the force, so formula is F is equal to G m1 m2 divided by d square, where m1 is the mass of the first ball, m2 is the mass of the second ball, and d square is the distance between the center of these two bodies. And G is taken to be as constant, gravitational constant, having the value of 6.67 into 10 to the power minus 11. Let us put the values. So here we go. The value of G is 6.67 into 10 to the power minus 11 into 1000 divided by 0.5 whole squared. When we take multiplication of these two thousand, this thousand, let me show it to you. This thousand and this thousand, when they multiply, basically that will be equal to 10, 0, 0, 0, 0, 0, 0. How many zeros are there? 6. So we can write it down as 10 to the power 6. And this way it is much more easier for us to write the whole thing. So it is 6.67 into 10 to the power minus 11 into 10 to the power 6 divided by 0.5 whole power squared. When we basically put that value in the calculator, we get 26.68 into 10 to the power minus 5. And when we solve it, this point basically, this point right over here, this point goes to the next point. That means it travels to the next point, and we'll basically write this in scientific form like 2.6 into 10 to, 2.67 into 10 to the power minus 4, because 1 was added onto one side. That means you can write it like this. In this case, you can say, if you put point over here on after the 2, you can multiply with 10 to the power 1. So 1 is plus and 5 is minus, so you can do it like this, minus 5 plus 1, so you can write it out like 10 to the power minus 4. And that is why I've written over here in scientific form 2.67 10 to the power minus 4. Moving on to the next question, question number 2, which says the gravitational force between two identical lead spheres kept at 1 meters apart is 0.006673 newtons. Find their masses, each of 10,000 kilograms each. Now in this case we have the force and we need the masses to be figured out. In this case, the mass of this sphere, which is of lead, and mass of this sphere, which is also made up of lead, and we have the distance between the two spheres, which is of 1 meter. But the force of attraction is still there, so they are attracting each other. So for that, let us look at the data. The data which is given to us, the distance between the ball D is 1 meter. The gravitational force is 0.006673 Newton. The mass of each ball we have to calculate. The gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. We have the formula, but before we put the values into the formula, let's say, because it is written over here identical, so we can say that both of the masses are same. M1 is equal to M2, which is equal to a certain mass M. Now in this case, When we put this value in the formula, it will be F is equal to gm1 m2 divided by d square. Or instead of putting m1 m2 again and again, we can simply put down simply m squared. That means that's the whole case. So m1 m2 will become m multiplied by m, it will become m squared, and that's why I have put m squared over here. F is equal to 0.00673 is equal to 6.67 times power minus 11 into m square, that means mass square divided by 1 square. So taking all the values to the other side, because we want to calculate the mass, find their masses. So m square will be equal to 0.006673 divided by 6.6 into 10 to the power minus 11. Now in this case, we'll take the 11 to the top side. That means that it will become the numerator from the denominator. M square is equal to 1 into 10 to the power minus 3 into 11. That means when it was in denominator, it was minus 11. When it goes up, it will become positive 11. So here the mass of both will be equal to m square is equal to 10 to the power 8. That means the total mass is 10 to the power 8 kilograms. But we have to find the mass of each. So what we have to do for that, we have to take the under root of both sides. When we take the under root both sides, it will be m squared is equal to 10 to the power 8 squared. So it will be equal to, if we basically do it like this, 10 to the power 8, and under root can be written as 1 over 2. So it can be written as 8 into 1 over 2, 2 ones are, 2 fours are. So it will be equal to 10 to the power 4 kilograms. So let us put this value now. It will be equal to m is equal to 10 to the power 4, or we can write it down like this. M is equal to 10,000 kilograms, or we can say hence mass of each ball is equal to 10,000 kilograms. Moving on to question number 3, it says find the acceleration due to gravity on the surface of Mars. The mass of Mars is 6.42 into 10 to the power 23 kilogram. Its radius is basically is 3,370 kilometer. The answer should come basically equal to 3.77 meter per second square. Now we have to find the value of g. The radius is given to us, which is 3,370 kilometer. The mass of the Mars is basically 6.402 into 10 to the power 23. Now in this case, we have to understand that we have to find the value of g. The mass is given to us, which is 6.42 into 10 to the power 23 kilograms. The radius of the Mars is 3,370 kilometer, or we can say 3,370 to 10 to the power 3 meters. So instead of kilo, I'm writing down 10 to the power 3. Now, in this case, we'll say the gravitational force on the surface of Mars is gm. We have to find that value. For that, we have a formula: gm is equal to m, or mass of the Mars, into g, which is gravitational force, divided by r square. From where did we get it? If we have a mass is equal to gravitational force, which is m, which is the mass of the Mars, and mass of that object divided by the distance between the object and the Mars, which is very little. So we say that it is the radius of the Mars. So this m and this m basically cancels out. What is left behind? It is the gravitational acceleration of Mars. From that formula, from that derivation, we found out the value. Let us put in the values. The value of g basically is, as we know, is 6.67 right over here. 6.67 into 10 to the power minus 11. The mass of Mars is given to us is 6.42 into 10 to the power 23, and the radius of Mars is also given to us is 3,370 into 10 to the power 3 whole squared. Now, in this case, when we put in the values, it will be g is equal to 6.67 into 10 to the power minus 11 into 6.42 into 10 to the power 23, and when we take square of this one, what do we get? We get 42.82 into 10 to the power 12 divided by 1, 11356,900 into 10 to the power 6, because we are taking square in this case. Now, if we basically put this value in the calculator and find out the values of g, it will be turning out that it is equal to 3.77 meter per second, which is the required answer over here. So the value of g in this case, if somebody is placing something over here, the value of g in this case will be 3.77 meter per second square. So it is much less than Earth, which has the value of g equal to approximately 9.8 meter per second square, or approximately 10 meter per second square. Now moving on to question number 4, which says acceleration due to gravity on the moon is 1.62 meter per second square. The radius of the moon is 1740 kilometers. Find the mass of the moon. Now we have to find the mass of the moon. Here we have a body and it is falling down because the value of g is very low as compared to the mass or the value of g of earth, which is the g value of g of moon is 1.6 into 10 power less is 0 meter per second square. Now, the radius of the moon is given to us is 1740 kilometers, and we have to find the mass of the moon. Now we are going to find out the mass. We have the solution. The gravitational acceleration is given to us, which is 1.62 in meter per second square. The radius of the moon is given to us is 1740 kilometers, is equal to 1740 into 10 power 3 meters. Again, I have converted to kilometer into meters so that it is represented in SI units right over here. Now in this case we have to find the mass of the moon. The formula again is the mass of the moon is equal to radius m into gm divided by g. Again the formula is when the weight of the body, let's say this body which has a mass m, is equal to the gravitational force of the moon, which is equal to g mass of the moon into the mass of the body divided by the distance between the two, or we can say the mass is very less as so distance is very less as compared to the radius of the moon. So we'll take the radius of the moon, which is rm squared. So here again the mass basically cancel on both sides. We have to find this mass cancel, this is still there. So the mass of the moon can be written as g into r squared, which is the mass of the moon, divided by capital G. So this is the formula to find the mass of the moon. Now in this case we have the formula now. Now we just have to put in the values. So the radius of the moon, which is 1740 into 10 to the power 3 whole squared, into the value of g, which is 1.62, divided by the value of g, which is 6.6 into 10 to the power minus 11. Putting in the values and taking square. So when we put in the values and taking square of these two over here, it will be squared, as well as the square of 3 10 to the power 3 is going to be 10 to the power 6 multiplied by 1.6 divided by 6.6 into 10 to the power minus 11. Now in this case when we multiply, we found out the value to be 73522.9.13 into 10 to the power 6 into 10 to the power 11, because when this 11 goes up it becomes positive. So we have moved this decimal to make it a scientific form. So it moved 1, 2, 3, 4, 5. So it moved 5 digits towards the left. So 10 to the power 5 written over here. So that it has increased. So we can write it down as 7.35 into 10 to the power 5 into 10 to the power 6 into 10 to the power 11. So 5 plus 6 is 11. 11 plus 11 is 21. So we can write it down as 7.35 into 10 to the power 21. And here we go. Sorry, not 11 plus 11 is 22. Sorry. So it will be equal to mass of the moon will be equal to 7.35 into 10 to the power 22 kilogram, and that is our mass of the moon. Now, hence mass of the moon can be written as 7.35 into 10 to the power 22 kilograms, and that is our answer as well. Moving on towards the next question, which says calculate the value of g, that means gravitational acceleration, at the height of 3,600 kilometers above the surface of the earth. Its answer should come 4 meter per second square. So here's our earth, and we are taking a mass which is a box approximately 3,600 kilometers away from the surface of the earth. So we have to find the value of g at that point. So solution says we have the height, which is 3,600 kilometers. We have the value of g, which is we have to find the value of g at this height, and the radius of the earth, which we'll know, is 6,400 kilometers, which is equal to 6.4 times power 3 meters, because it is in kilos. Or so we can write it down like this, because it is in kilos, we can still write down in kilos, or we can say 6.4 into 10 to the power 6 meters. This is the right answer. This is the radius of the earth, and mass of the earth is basically 6 into 10 to the power 24 kilograms. Formula says that g is equal to me divided by r h whole squared. Again, the formula is the same. The mass of the body is equal to the gravitational force, which is equal to g m e into m divided by r plus 8. That means the height it is, or you can say as whole of this is small r. So this m and this m basically cancels out. The value of gh is gm e over r plus r h whole square. Now let us put the values. So for this we have to find the total height of the body from the center of the earth, which is equal to r plus rh. The center of the earth is from here. So what is the radius? The radius was basically 6,400 kilometers plus 3,600 kilometers, so it will be 10,000 kilometers, and you can say 10,000. This is one more zero over here, so it is 10,000 kilometers into 10 to the power 3 meters, because we have converted the kilometer into meters over here. Moving on to the values. So instead of writing 4 zeros, we can say 10 to the power 4 into 10 to the power 3. It will be 10 to the power 7 meters. So putting this value in this formula, the value of r plus h, we get g is equal to 6.6 into 10 to the power minus 11, 6.0 into 10 to the power 24, which is the mass of the earth, and the value of r plus h is equal to 10 to the power 7. Taking whole squared, what do we get? We get 40.02 into 10 to the power minus 11 into 10 to the power 24, which is the mass of the earth. 10 to the power 24 divided by 10 to the power 7 whole squared, and we get 4.02 into 10 to the power minus 11 and 10 to the power 24. 24 divided by 10 to the power 14, because we are taking square of 7. GH is equal to 40.03 into 10 to the power minus 11 into 10 to the power 24 into 10 to the power minus 14. G is equal to 40.03 into 10 to the power 24 into 10 to the power minus 25. When we solve this 10 to the power 24 and 10 to the power minus 25, it will be equal to G is equal to 40.03 into 10 to the power minus 1. So in that case, if this is 10 to the power minus 1, we'll take the point to the other side, it will be 4.003 into nothing, basically 10 to the power nothing, 0. So the value of G can be given to us as approximately 4 meter per second square. The value of G at on 36 kilometer above the height of the surface of the earth is 4 meter per second square, which was our required answer as well. Moving on to the next question, which says find the value of G due to the Earth's geostationary satellite. The radius of geostationary orbit is 48,700 kilometers, and the value of G at that point is 0.17 meter per second square. So this is our Earth, and we have a satellite over here. Let's squeeze it down to the size and move it to 4,870 kilometers. So here's the height plus the radius, and we have to find the value of G. Here it goes, here's the revolution, and we have to find the value of G at that point. So the radius of geostationary satellite is R, which is 4,870 kilometers. So the height from the Earth is 4,230 kilometers. The mass of the Earth is basically 6 into 10 to the power 24 kilogram, and the radius of the earth is basically 6,400 kilometers. Now what will be the total height of this satellite? That means the radius of the earth as well as from the height from the earth as well. Now in this case, the values are turn out to be, first we have to find the value of r plus h, which we have r plus is equal to 64 into 442 42,300, sorry. And when we put in the values, we get the total r distance from the center of the earth, which is 48,700 kilometer. We can say 4.87 into 10 power 7 meters. Now putting this value of RH in this formula to find the value of G, what do we get? We get GH is equal to 6.67 into 10 power minus 11 into 6.42 into 10 power 24 divided by the value of R plus H, which was 4.8 into 10 power 7 right over here, and taking square of it. So what is the answer for this one? Let's solve this one. So we'll take first square of this one, first part, which is the 4.8 into 7. Sorry, 4.87 into whole squared multiplied by the square of 10 to the power 7, which is 14, and the value of G is written as it is, which is 6.67 into 10 to the power minus 11, and the value of mass of the earth, which is 6.00, actually is 6.00 into 10 to the power 24. Now, when we put in the values, what do we get? We get 40.02 into 10 to the power minus 11 into 10 to the power 24 into 10 to the power minus 14 divided by 23.72. Where does this 14 come from? Over here it was positive. When it got up, it became negative, and that's how we are solving it. So the value of G at that point will be in 1.7 into 10 to the power minus 1 meter per second square. So it is minus 1 over here. Already we have written it in a scientific form, but we have to write it in our required answer, which is the same as given, which is equal to 0.17 meter per second square. So our answer is right here. The value of G for a geostationary relay is 0.17 meter per second square. So over here the value of G is given to us is 0.17 meter per second square. Moving on to the next slide, it says the value of G is 4 meter per second square at a distance of 10,000 kilometers from the center of the earth. Find the mass of the earth at this point, and approximate mass of the earth is given to us, which is 5.99 into 10 to the power 24 kilograms. So the value of G is given, and the distance from the surface of the earth is also given. Sorry, the distance of 10,000 kilogram from the center of the earth. That means the radius is also given to us. From the center part of the earth, the distance from the center of the earth is given to us is 10,000 kilometer, or we can say 10,000 into 10 to the power 3, or we can say 10 to the power 7 meters. So value of G is 4 meter per second square. We have to find the mass of the earth. The formula is simple. The mass of the earth is equal to R square is equal to Gm divided by G. So this whole thing is basically R, and it contains the basically radius as well as the height of the body attained from the surface of the earth. Putting in the values, what do we get? We get me, that means the mass of the earth is equal to the radius, which is equal to 10 to the power 7 whole squared into value of G, which is 4, divided by the value of G, which is 6.67 into 10 to the power minus 11. When we solve it, we'll get 10 to the power 14, because 7 multiplied by 2 is 14. Here we go, and the value of 4 as it is, the value of G is 6.67 into 10 to the power minus 11. So we get approximately equal to 0.599 into 10 to the power 14 into 10 to the power 11. We get basically in this case 0.599 into 10 to the power 25. So in this case, we are going to say that it is approximately 25. So this answer is basically something wrong. So because this is 11, when it got up, it will be approximately equal to plus 11. And let's see if we can calculate it over here. That 4 divided by 6.66 is it equal to 0.59, or point is different, maybe 0.5 divided by 4. Let us calculate. In this case it is 0.59 is the answer, and we can calculate it as 4 divided by simply 6.67. So it is 0.599, which is correct, and all the other things are basically correct. So this is the right answer. ME is equal to 0.599 in 10 to the power 25. So this you have to correct. It is 25. The mass seemed to be more as compared to before when it is taken 10,000 kilometers away from the surface of the Earth. Moving on, the mass of the Earth is basically 5.99 into 10 to the power 24. If we take the point over here to the other side, let's say over here, it will be 5.99 in 10 to the power 24. And this answer is now correct basically because this is 5.99 in 10 to the power 24. So if we take the digit to the right hand side, the 10 to the power minus 1 will be there, and it will be 5.99 in 10 to the power 24. And the mass of the Earth is equal to 5.99 in 10 to the power 24, and that is the correct answer over here as well now. That is our required answer. Moving on to the next question, it says, at what altitude the value of G would become fourth than on the surface of the Earth? Now, as we are moving this object to the certain height, so its value of G decreases. He says, at what point will the value of G become one-fourth? So here's the radius of the Earth. We have the value of G where it becomes one-fourth. The radius of the Earth is 6.4 into 10 to the power 6 meters. The mass of the Earth is taken to be 6 into 10 to the power 24 kilograms. Putting in the values, we get G is equal to ME, which is the mass of the Earth, into G divided by R plus H whole squared. And when we put in the values, so R plus H is the whole square is equal to ME G over GH, because this is the G which we are changing. So instead of writing this G, we can write it down as G4, G divided by 4, because it is one-fourth of the value at certain height. We have to find that height now. R plus H whole square is equal to 4ME into G divided by small g, which is the gravitational acceleration. Putting in the values, R plus H whole square is equal to 4, which is taken as it is. Mass of the Earth is basically approximately you can say 6.0, not 5, 6.0 into 10 to the power 24. The value of G is 6.6 into 10 to the power minus 11 divided by 10. Putting the values, R plus H is in whole square is equal to 160.152 into 10 to the power 10 to raise power 24 minus 11 minus 1. Now, if we calculate it, we get R plus H whole square is equal to 160.152 into 10 to the power 24, because we can see 24 minus 11 or minus 1 will be equal to 12. So 12 minus 24 will be 12. So here we can write down like this. Let me clear this out for you. So here we can write down like this: 24 minus 12 is equal to 12. So 160.152 into 10 to the power 12. So taking under root on both sides to cut down the square, we get this square will cancel out with this under root. R plus H is equal to under root 160.15 into 10 to the power 12. R plus H is equal to 12.65 into 10 to the power 6. So we have to find the value of H because we already know the value of R. So H will be equal to 12.65 into 10 to the power 6 minus R, and we know the value of R, which is equal to 6.4 into 10 to the power 6, which is written over here. So when we cancel out these values, what do we get? We get approximately the value of R, almost the values of R, which is equal to H is equal to 6.25 into 10 to the power 6 meters. So it is approximately the value of R. Hence the height is approximately equal to the one radius of Earth. So what do we do over here? So if we want the body to get one-fourth value of G, we have to move it a same distance, or approximately the same distance of R. So here we go. If we move the same distance to the R, now at this point the value of G will be one-fourth the original value of G, which was at of Earth over here. Now this is the concept which is given to us. This is the RH over here, and the value of G, as all of we know, that is 9.8 meter per second on the surface of the Earth. But as we move away from the Earth, the value of G will decrease one-fourth time if it is moved R distance from the Earth. Moving on towards next question, which says a polar satellite is launched 850 kilometers above the Earth. Is final find its orbital speed. Now here's a satellite in front of us. Here's a satellite. Let us squeeze it down to the size, and we have to find the orbital speed when it is 850 kilometer from surface. Here it is, 850 kilometers from the Earth's surface. Now, as it is revolving around the Earth, what is the orbital speed for this one? We have to find the orbital speed, which is V naught. What do we have in data? The data is given to us is polar satellite is h is equal to 850 kilometer. The radius of the Earth is 6,400 kilometers. The orbital speed is given to us, which we have to find out basically, which we don't know. The formula for that one is V naught is equal to under root G h into R plus R, which is equation number 1. To find that, first we have to find the value of G at that point. What was the value of G at that point? For that we have Gh is equal to me, which is the mass of the Earth, G gravitational constant, which is 6.67 into 10 power minus 11, divided by R plus H whole square. Putting in the values, we get R plus H is equal to 6,400 plus 850. We get the value of 7,250 kilometers, or we can say 7,250 into 10 power 3 meters, or 7.2 into 10 power 6 meters. So this is the total distance from here to here, from the center of the Earth to the point where the satellite was being put. Now, by putting this value of the value of R plus H in this formula, we get the value of G, which is 6.6 into 10 power minus 11 into 6 into 10 power 24 divided by 7.2 into 10 power 6 whole square. We get the value of G, which is 6.6 into 10 power minus 11 into 6.0 into 10 power 24 divided by 5, 52.5625 into 10 power 12, because we are multiplying psi 6 into 2, which is equal to 12. We get the value 0.76 into 10 to the power minus 11 into 10 to the power 24 into 10 to the power minus 12. So we have 24 minus 11 and minus 12. So minus 12 and minus 11 will become minus 23. Minus 23 minus 24 will equal to 1. So the values will become the value of G is 0.7613 into 10 to the power 1. And when this 1 or 10 multiply with this value, 0 will basically be removed, and the digit will move 1 digit towards 7. So it will become 7.613. Yes, 7.6 is a round of number. So the value of G at this point will be 7.6 meter per second square. Now we have to put this value of G in this formula to find the orbital speed in this case now. Hence, putting the value in above equation 1, that means we have to put this value in this equation. So what do we get? Orbital velocity is equal to under root 7.6 into 7.25 into 10 to the power 6. When we put in the values, it will be V naught is equal to under root 55.19 into 10 to the power 6. Taking under root, we'll get the orbital velocity to be 7.43 into 10 to the power 3. Or we can say it as orbital speed is equal to 7,431 meter per second, and that is our required answer as well. So that is the required answer for this numerical. Moving on towards the last numerical of this chapter, and that is our orbital speed. And the last numerical says a communication satellite is launched 42,000 kilometer above from the Earth. Find its orbital speed, and its answer should come 2,876 meter per second. Now here's our Earth, and here's the satellite which we were talking about, and it was moved 42,000 kilometer away from the Earth's surface. Now in this case we have the radius also, so it is moving from the center of the Earth, and we have to find its orbital speed as well. The solution is given to us. The height of the from the Earth is 42,000 kilometers. We can write it down as 42,000 times power 3 as well. Orbital speed, which we have to find. The mass of the Earth is 6 into 10 power 24 kilograms. The radius of the Earth is 6,400 kilometer. The orbital speed which we have to find can be found out by this formula, that where V naught is equal to under root GH into R plus H. Now in this case we have to find the value of G at that point, because we don't know the value of G at that point. What would be the value of G at this position when the satellite was taken 42,000 kilometers away from the surface of the Earth? Now GH is equal to ME into G divided by R plus H whole squared. For putting in the values, when we get R plus H, which will go to 6,400 plus 42,000, what do we get? 48,400 kilometer, or we can say 48,410 to the power 3 meters, because kilometer has been converted into meters now. The R plus H can be simply written as noun scientific form, which is 4.84 into 10 to the power 7 meters now. Putting in the values of R plus H is in this formula, which is the value of G, to find the value of G. So GH is equal to 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 divided by 4.8 into 10 to the power 7 whole squared. We get 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 divided by 4.8 whole power, and taking square on 10 to the power 7, we get 10 to the power 14. We get from here the value of G is equal to 6.67 10 to the power minus 11 into 6 into 10 to the power 24 divided by 23.4256. The value of G at this position will be 1.7 into 10 to the power minus 11, or we can say the value of G at this point will be equal to 0.17 meter per second square. So the value of G at this position will be equal to 0.71 meter per second square. But this is not the end. We have to find the orbital velocity for this. We only find out the value of G. Now we are putting the value of G in this equation. Now let us put the value of G in the equation number 1. Putting values of in equation number 1, what do we get? The value of G is 0.1, and the R plus H will be equal to 4.84 into 10 to the power 7. So this is not 107, this is 10 to the power 7. So when we put in the values, the value of orbital velocity will be equal to 2876 meter per second, and that is our required answer as well. So in this case, the orbital speed will be given to us in a circular form when the satellite will revolve around the Earth. I hope you understand and enjoy today's lecture. Inshallah, we'll meet again. Allah Hafiz.